Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Fiber optic cabling represents one of the most powerful and reliable transmission media in networking. Unlike copper cables that carry electrical signals, fiber optic cables transmit data using light. This light travels through a highly precise glass or plastic core, enabling extremely fast data rates and long transmission distances. Because fiber uses light, it is immune to electromagnetic interference, can operate across much greater distances than copper, and supports the bandwidth needs of modern enterprise, service provider, and data center networks. It has become the standard choice for backbone links, wide area networks, and high-performance infrastructure. Fiber optics is a critical topic in the Network Plus exam and appears throughout media and infrastructure-based objectives. You may be asked to identify fiber types, choose appropriate connectors, or determine the best media for long-distance, high-bandwidth scenarios. Questions may also focus on characteristics like connector color, bend radius, and transmission mode. Whether the scenario is a building-to-building uplink or a WAN trunk from an internet service provider, understanding fiber is essential for answering correctly and supporting real-world deployments. The structure of a fiber optic cable is both simple and highly engineered. At the center is the core, which is the light-carrying portion of the cable. The core is typically made of ultra-clear glass and can be as narrow as 8 microns for single-mode fiber or as wide as 62.5 microns for older multi-mode variants. Surrounding the core is the cladding, a layer with a slightly lower refractive index that reflects light back into the core using total internal reflection. This keeps the signal contained as it travels through the cable. Around the cladding are layers of buffer material and an outer protective jacket, which guard against physical damage and provide mechanical stability. Fiber optic cabling offers several significant advantages over copper. The most notable is bandwidth. Fiber supports vastly higher data rates, with the potential for terabit-level speeds, depending on the transceivers and light sources used. Fiber also supports longer transmission distances without requiring signal regeneration. Single-mode fiber links can reach tens of kilometers, while multi-mode fiber spans shorter but still substantial distances. Additionally, fiber is completely immune to electromagnetic interference, making it ideal for noisy environments, industrial zones, and secure facilities where data isolation is critical. There are two primary classifications of fiber optic cable: single-mode and multi-mode. Single-mode fiber uses a very narrow core and transmits light in a single path, or mode. This results in lower signal loss and higher bandwidth over longer distances. Single-mode fiber is commonly used in long-haul telecom, ISP backbones, and inter-building links in campus environments. In contrast, multi-mode fiber uses a wider core and allows multiple modes of light to travel simultaneously. This makes it more affordable and easier to work with, but it limits its range and bandwidth. Multi-mode fiber is common in short-distance applications such as patch runs, local distribution, and inside data centers. Fiber optic connectors come in a variety of types, each suited to different environments and preferences. C connectors are small form-factor connectors with a push-pull latch, popular in modern enterprise and data center deployments due to their compact size. SC connectors use a similar push-pull mechanism and are larger, making them easier to handle but less space-efficient. ST connectors feature a twist-lock design and are more common in legacy systems. MTP connectors and their related MPO standard are high-density multi-fiber connectors used in environments requiring multiple parallel fibers, such as 40 or 100 gigabit links. Fiber cabling is also categorized based on whether it is simplex or duplex. A simplex fiber cable has a single fiber strand and is used for one-way communication. A duplex fiber cable contains 2 fiber strands, one for transmitting and one for receiving, which enables full duplex communication. Duplex fiber is more common in bidirectional communication systems such as Ethernet, where simultaneous send and receive operations are needed. The type used depends on the transceivers and the nature of the communication required between endpoints. Different types of light sources are used depending on the fiber mode. Multi-mode fiber typically uses light-emitting diodes or vertical cavity surface-emitting lasers, VCESLs. These light sources are less expensive and generate a broader light spectrum suitable for shorter multi-mode applications. Single-mode fiber requires highly focused narrow bandwidth lasers, which provide the precision and power needed for long-range transmission. The choice of light source impacts signal strength, transmission range, and the quality of the optical signal over time. Installing fiber optic cabling requires careful attention to physical handling. Fiber is more fragile than copper, particularly the glass core, and must be protected from sharp bends, excessive tension, and physical damage. Most manufacturers specify a minimum bend radius that must be maintained to prevent microfractures and signal loss. Routing cables through proper trays, avoiding pinch points, and supporting cable runs helps preserve signal integrity. Even small imperfections or excessive bending can cause optical attenuation or complete signal loss, especially in high-speed links. Cleanliness is another major factor during installation and maintenance. Fiber connectors must be kept free of dust, oil, and debris. Contaminated connectors are one of the most common causes of signal problems in fiber networks. Technicians should use proper inspection tools, including fiber scopes and lint-free cleaning kits, before making any connection. Inspecting and cleaning both the connector and the port ensures that light can pass through the connection point with minimal loss or reflection. Safety is also important when working with fiber optics. Unlike copper cabling, where the risks are mainly electrical, fiber optics introduces the risk of eye damage from invisible laser light. Never look directly into the end of a fiber cable connected to an active light source. Use inspection tools with safety filters instead. Additionally, broken fiber strands can be hazardous if they pierce the skin or become embedded in clothing or work surfaces. Always dispose of fiber shards properly. Use safety glasses when cleaving fiber, and avoid touching connector tips with bare hands. Fiber is especially well suited as a backbone media. It is often used to link network switches across buildings, to connect floors in a high-rise, or to create high-capacity pathways between aggregation switches and data centers. Its high-speed, low-latency, and long-distance capabilities make it ideal for carrying large volumes of aggregated traffic. In structured cabling systems, fiber often complements twisted pair by handling high-volume transit links, while copper serves endpoint devices. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. The outer jacket of a fiber optic cable is more than just a protective shell. It plays a vital role in defining how and where the cable can be used. Cable jackets are rated for different environmental conditions, such as exposure to moisture, sunlight, extreme temperatures, or fire. Indoor fiber cables often use polyvinyl chloride (PVC) jackets, which are cost-efficient but emit toxic fumes if burned. For fire-safe environments such as air handling spaces or ceilings with active ventilation, plenum-rated jackets are required. These are labeled CMP and are designed to resist flame and produce minimal smoke. Riser-rated jackets labeled CMR are used for vertical runs between floors and offer moderate fire resistance. Outdoor fiber may use UV-resistant and waterproof jackets and may include an additional layer of armor for protection against crushing or rodent damage. One of the easiest ways to distinguish fiber optic cable types in the field is by their color coding. Jacket colors are often standardized to indicate the mode of the fiber. For example, yellow typically indicates single-mode fiber, while orange is used for older multi-mode cables. Aqua is the color most commonly associated with newer laser-optimized multi-mode fiber, which supports higher data rates and longer distances using VSEC-L light sources. These color codes help technicians and installers quickly identify fiber types during deployment, troubleshooting, or upgrades. While color alone is not definitive, since custom jacket colors may be used for aesthetic or labeling reasons, it remains a useful visual clue when working with a mix of media types. Fiber optic technology is a cornerstone of modern WAN and ISP network infrastructure. Service providers use fiber to connect central offices, aggregation switches, and distribution hubs. Long-haul fiber links span thousands of miles across continents and under oceans, forming the backbone of the global internet. Fiber reduces the need for signal repeaters and allows for massive bandwidth over long distances with low latency and minimal signal loss. As fiber continues to replace legacy copper systems, even residential connections are increasingly being delivered through fiber-to-the-home technologies. Despite its many advantages, fiber optic cabling does come with limitations. First, it tends to have a higher upfront cost than copper cabling. While fiber prices have decreased over time, the installation process often requires specialized tools and trained technicians. Fusion splicers, precision cleavers, and optical test equipment add to the investment. Second, fiber is more fragile than copper. The glass or plastic core can break if the cable is bent too sharply, crushed, or improperly terminated. These physical limitations require careful planning, proper cable routing, and protective enclosures to preserve long-term reliability. Splicing and terminating fiber optic cables require precision and the right tools. Mechanical splicing involves aligning two fiber ends and using a special gel or connector to hold them in place. While quicker and cheaper, this method is less reliable and has higher signal loss than fusion splicing. Fusion splicing melts the two fiber ends together using an electric arc, creating a nearly seamless bond with minimal optical loss. This process is highly accurate but requires expensive splicing equipment and precise handling. In addition to splicing, fiber terminations may use pre-polished or field-polished connectors, each with their own advantages in terms of speed, cost, and precision. Once fiber is installed, fiber patch panels and enclosures play an important role in maintaining the integrity and manageability of the cabling system. These enclosures organize fiber strands, provide termination points for connectors, and offer protection against mechanical damage. Patch panels are typically labeled to indicate the connection paths between different switches, routers, or servers. These panels also help preserve the required bend radius of each cable, ensuring that fibers are not kinked or stressed. Cleanliness within patch panels is especially important. Dust, oil, or dirt on a connector can degrade signal quality or lead to complete link failure. Testing fiber optic connections is a critical part of installation and maintenance. Optical power meters measure the amount of light being received at the far end of a fiber link. Light source testers are used in conjunction with power meters to test end-to-end continuity and signal loss. Optical time domain reflectometers are advanced tools that send pulses of light down the fiber and measure reflections caused by faults, bends, or breaks. These tools are particularly useful in troubleshooting long fiber runs, as they can pinpoint the exact location of issues based on the time it takes for reflected light to return to the tester. The Network Plus exam expects you to recognize fiber optic connectors and match them with their appropriate use cases. You may see questions that ask you to identify a connector such as LC, SC, or ST based on a diagram or photo. Other questions may involve choosing the correct mode, single mode or multi-mode, for a scenario involving distance or bandwidth requirements. You may also be required to determine the appropriate cable type or jacket rating for an installation in a plenum ceiling or outdoor environment. Fiber topics often appear in WAN or backbone connection scenarios, where high bandwidth and long distances are emphasized. Being able to interpret a fiber optic network diagram is another important exam skill. You might be presented with a diagram showing fiber connections between buildings or between a core switch and distribution switches and asked to identify the correct cable type, connector, or termination point. The ability to analyze the purpose of each link and recognize the supporting fiber type is essential not only for the exam, but also for anyone working in network design or structured cabling. In practice, fiber continues to grow in importance as bandwidth demands increase. The expansion of cloud computing, 4K and 8K video, virtual reality, and data analytics all push the limits of copper cabling. Fiber offers the future-proof performance necessary to support these technologies, especially as multi-gigabit internet becomes more common. While the initial investment may be higher, fiber reduces long-term operational costs by eliminating the need for repeaters, lowering power usage, and supporting much higher user densities over the same infrastructure. Fiber's use is not limited to internet providers or data centers. It is increasingly deployed in corporate buildings, hospitals, educational campuses, and even residential developments. With pre-terminated cables and modular installation kits now available, fiber installation has become more accessible than ever. Technicians with fiber skills are in high demand, and knowledge of optical systems is a valuable addition to any network professional's toolkit. Whether you're supporting a small office or a global enterprise, understanding fiber helps you design and maintain networks that are resilient, scalable, and ready for future demands. In summary, fiber optic cabling is a core technology in modern networking. Its ability to carry light instead of electrical signals allows for unmatched performance in terms of speed, distance, and signal quality. Understanding the structure of fiber cables, the differences between single-mode and multi-mode, the connectors used, and the tools required for installation and testing will help you master the physical layer and confidently answer fiber questions on the Network Plus exam. Fiber is no longer a niche skill. It is a necessary part of network architecture in nearly every environment. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.